Hi, let's go over the theory behind experiment 2, quantum nature of light. Hold on a second while I switch over to the iPad. Okay, here's the experiment in its simplest form. We have a source of light, a rather special source called a single photon source. And our mental picture here is that this creates single photons, which are sent to a 50-50 beam splitter. We have detectors here, a transmit detector and a reflect detector, which measure to see if an excitation reaches the detectors. And the rules of quantum mechanics tell us that each time we send in a single photon, that one of these detectors will fire, but not the other. And we're carrying out this experiment because we think this is an experiment that will distinguish very cleanly between the photon model of light from quantum mechanics and the classical model of light as a continuous electromagnetic wave. So that's the theory we want to investigate. Okay? Okay, to talk about this more carefully, let's take a quick look at these detectors. These are called photon counting detectors, and the normal way to think about it is that they're sensitive enough that if they absorb a quantum of light, a photon, they'll produce a distinguishable pulse. And so we can simply count the number of pulses that come out of the detector per second to find the number of photons that strike per second. But we have to be a little bit careful. The presence of a photon counting detector which produces an output which consists of a series of pulses, is not in itself a proof that light consists of quanta, that light is absorbed as quanta of energy. If we look more carefully at how these work, we can make up the following picture. These are these particular devices are called avalanche photodiodes. Similar devices are photomultiplier tubes. In any case, the way that they work is that when light is absorbed, a quantum of light should have enough energy to ionize an electron within the detector to promote it into a free state. This electron then accelerates in a strong electric field inside of the detector, and as it accelerates, it ionizes more electrons through a process called impact ionization. That's the avalanche in the avalanche photodiode. And then the result is that a big pulse of current exits the detector, a pulse of current that's large enough for us to detect. Okay? Now, the pulse represents some kind of quantization, but if you look carefully, you'll notice it's actually the electron that's quantized, not the electromagnetic wave. In other words, this would also work if we had classical light, which just occasionally, through some random process, is able to ionize electrons. We'd still get pulses each time an electron was ionized. Okay? So it's not enough just to have photon counting detectors in our experiment emitting pulses. We need something more. And in particular, what we need is we need to be able to observe the anti-correlation that we expect in the photon picture. The fact that under some conditions, when we do this experiment, we should expect that if that one of these detectors may fire or the other one should fire, but they should never fire simultaneously, because a measurement of which path the photon takes can only have one result, either reflect or transmit. And that's different than what we'd expect for electromagnetic waves. It's a little bit of a subtle point. It seems obvious, but there's a little bit more that we want to investigate. So we'll talk about that next. 1 second. Okay. To describe the difference between the classical case and the quantum case, we're going to look at something called, it's a mouthful, called the second order coherence between the electric fields for the reflected and transmitted waves. So we're going to write this as G2 TR, okay? And we're going to define this as the following. It's the average of the product of the intensities or the signals from the transmit and the reflected waves divided by the average of the intensity of the transmitted wave times the average of the intensity of the reflected wave. Okay? This is the quantity here. And a little thought will show us why this is an important quantity. Okay? Again, notice what we have. On the numerator, we have the average of the product of the two intensities. But in the denominator, we have the product of the averages. And that's something quite different, as you'll see in a moment. Here, let's investigate what we expect for the quantum picture, where we have photons and where in the single photon case, if a photon is detected at the transmit receiver, it cannot be detected at the reflect receiver and vice versa. So in this case, we expect perfect anti-correlation between the outputs. That means that any time that the transmit intensity is non-zero, the reflect intensity will be zero, or vice versa. And so the product of these will be zero. That means the term in the numerator, the average of the product, will always be zero. Oops. On the other hand, the average of each detector signal is not zero. Perhaps under the conditions of our experiment, each of these produces a pulse 50% of the time. Then the average of each one of these would be 50%. And so the product of those would be 25%, not zero. And so the second order coherence would be zero, okay? That's the photon case. However, the case for a classical wave would be different. Here, 1 second. Okay, the case for the classical wave, as I said, would be different. Because here, we expect that the transmit intensity and the reflected intensity are related to the incident intensity, the intensity of light incident on the beam splitter, which is a continuous quantity. So IT might be written as the transmission coefficient times I0, and IR might be given as the reflection coefficient times I0. Okay? Where I0 is the incident intensity. And we'll assume for the moment that T and R are stable, steady quantities, okay? If I0 is also steady in time, then it's of course quite simple to work out G2TR. It would just be T I0 times R I0 average divided by T average of T I0 times R I0. And now, since T and R are constants, you'll notice they factor out from the expression. And so we get the average of I0 squared divided by the I0 average squared. Okay? Okay. Now, there's a mathematical theorem that says that no matter what I0 is, and no matter how it varies in time, this product always has to be greater than or equal to 1. So classically, we'd find that the second order coherence always has to be greater than or equal to 1. And you can see that's quite different than the quantum prediction. So that's really the basis of this experiment. But let's just illustrate it with a couple of cases. And then I want to show you a simulation of the experiment that illustrates it as well. Okay? So first, suppose that I0 is a constant. Then you can see right away that in that case, G2TR would be 1. Okay? That's one of the limits of our expression. Well, that wasn't so exciting. Let's take another case. Let's suppose that I0 is equal to some other constant times cosine squared of omega t. Okay? So it's always positive, but it varies between 0 and a. Okay? And it oscillates with time. Like so. Okay? Then G2 would be, well, it's going to end up being a squared times the average of cosine squared squared divided by a squared times the average of cosine squared omega t times the average of that again. Okay? And as you probably can see right away, the average of cosine to the fourth omega t is not equal to the square of the average of cosine squared. Well, this is easy to work out. So this works out, so this is going to be, excuse me. Oh, 1 second. Okay. So this will be the average value of cosine to the fourth omega t divided by average value of cosine squared omega t squared. And I'll let you work this out, but if you don't mind, I'm just going to write down the answer and spare us the math. The average value of cosine to the fourth is 3/8. The average value of cosine squared is 1/2. And then we have to square that. And so the result is 3/2. So G2 in this case is 1.5. So now we have something that's greater than 1. So in the case where the result was steady, where the intensity was steady, no fluctuations, we got 1. But in the case where the intensity fluctuates, we get 1.5. Okay? But in both cases, it's greater than or equal to 1. And here's the important point. In contrast, quantum mechanics predicts that for the particular kind of light source we're going to use, that the second order coherence should be 0. Okay. Okay, I'm going to go ahead now and show you the simulation. So just hold on for a moment. We'll go to the next video.